Stars are among the most fascinating objects in the universe, and their formation is a process that spans millions of years, unfolding in regions that are both beautiful and chaotic. Every star begins its life within a molecular cloud, also called a stellar nursery or nebula, which is a dense concentration of gas, primarily hydrogen and cosmic dust. These clouds are incredibly cold, often just a few degrees above absolute zero, allowing the gas to remain in a fragile, diffuse state. Over time, disturbances such as nearby supernova explosions, galactic collisions, or even gravitational perturbations can trigger pockets of these clouds to collapse under their own gravity. This collapse initiates the birth of a protostar, the earliest observable stage of a star's life. As the cloud contracts, particles collide and coalesce, creating clumps of matter that slowly grow denser and hotter. In these regions, gravity pulls more and more gas toward the center, forming a core surrounded by a rotating envelope of material. This rotation often flattens the surrounding gas into a protoplanetary disk, which may eventually give rise to planets, asteroids, and comets. In some cases, multiple protostars form from the same cloud, creating stellar clusters that illuminate their surroundings and interact through complex gravitational forces. Observing these clusters provides scientists with invaluable insights into the conditions necessary for star formation and the diversity of stellar outcomes. As the core of the protostar grows hotter and denser, pressure builds up to the point where nuclear fusion can begin. Hydrogen atoms start to fuse into helium, releasing energy in the form of heat and light. This process marks the star's official entry onto the main sequence, the longest and most stable phase of a star's life. But before this stabilization, the protostar undergoes dramatic changes. Powerful stellar winds and jets emerge from the poles, blasting away excess material and influencing the surrounding nebula. These outflows can trigger the collapse of nearby gas pockets, creating new stars in a chain reaction, or they can disperse the remaining gas, preventing further star formation in the immediate area. In essence, the birth of one star can shape the formation of many others, making stellar nurseries highly dynamic environments. The size and eventual fate of a star are largely determined by the amount of mass it accumulates during formation. Small stars, known as red dwarfs, gather relatively little mass and burn fuel slowly, allowing them to live for tens to hundreds of billions of years. Medium-sized stars, like our Sun, strike a balance, sustaining steady nuclear fusion for around 10 billion years. Massive stars, on the other hand, consume their fuel rapidly, shining brilliantly but living only a few million years. The differences in mass also influence how stars interact with their surroundings. Massive stars exert strong gravitational forces and emit intense ultraviolet radiation that can ionize nearby gas, sculpting nebulae into striking shapes and even halting star formation. In some regions, stellar birth is not always a smooth process. Protostars often exhibit irregular luminosity as they gather material from their surrounding disks, and sudden bursts of energy can occur when large clumps of gas fall onto the forming star. These events can be observed as infrared flares, giving astronomers clues about the accretion process and the composition of the protoplanetary disk. By studying these early stages, scientists can also understand how planets may eventually form in orbit around the star. The alignment, size, and composition of these planets are influenced by the mass, rotation, and radiation of the newborn star, linking stellar formation directly to planetary systems. One of the most visually stunning aspects of star formation is the interplay between light, gas, and dust. As protostars ignite, they illuminate their surroundings, creating glowing regions known as H2 regions. These areas are often visible across vast distances and are captured in some of the most iconic astronomical images. Nebulae such as the Orion Nebula showcase the intricate filaments, dense knots, and vibrant colors resulting from the interaction of starlight with gas. Observing these formations allows astronomers to study the physical processes at work, from shock waves to radiation pressure, and understand how stars can influence the evolution of entire galaxies. Ultimately, the birth of a star is a remarkable story of gravity, motion, and energy. From a cold, diffuse cloud of hydrogen and dust to a shining beacon of nuclear fusion, each star represents a triumph of natural forces and cosmic timing. By examining these processes, astronomers gain insights not only into the origins of stars themselves, but also into the formation of planetary systems, the enrichment of the cosmos with heavier elements, and the interconnected cycles of creation and destruction that shape the universe. The birth of a star is both a singular event and part of a larger cosmic narrative, a dynamic, ongoing process that continues to sculpt the heavens we observe. Once a star reaches the main sequence phase, it enters the longest and most stable period of its life. During this stage, the star fuses hydrogen into helium in its core, producing a steady output of energy that balances the inward pull of gravity. For stars like our Sun, this phase lasts about 10 billion years, a period during which they shine consistently and maintain structural equilibrium. The star's mass determines how quickly it consumes fuel, with massive stars burning their hydrogen far more rapidly than smaller ones. Red dwarfs, for example, can last hundreds of billions of years, while the most massive stars live only a few million years. Despite this difference in lifespan, all stars eventually exhaust their core hydrogen, leading to dramatic changes in structure, luminosity, and size. As hydrogen runs out in the core, the balance between gravity and radiation pressure is disrupted. In medium-sized stars, the core contracts and heats up while the outer layers expand, turning the star into a red giant. In this phase, the star's luminosity increases, and its radius may expand hundreds of times larger than during the main sequence. This expansion can engulf nearby planets, as some of the outer layers drift away into space. The fusion processes become more complex, producing heavier elements like carbon and oxygen in shells surrounding the core. For massive stars, the situation is even more extreme, leading to a supergiant phase, where layers of fusion occur simultaneously, producing elements up to iron in the periodic table. The final stage of a star's life depends primarily on its mass. Low to medium mass stars, like our Sun, shed their outer layers gently, creating a glowing planetary nebula, while the remaining core compresses into a dense white dwarf. White dwarfs no longer undergo fusion. They gradually cool and fade over billions of years, slowly radiating their residual heat into space. This process represents a quiet and elegant conclusion to the life of an average star, leaving behind elements that can later participate in the birth of new stars, planets, and even life itself. Massive stars, however, die much more violently. After exhausting their nuclear fuel, they can no longer counteract the force of gravity, leading to a catastrophic collapse. The core implodes, and the outer layers explode outward in a spectacular supernova. This explosive event releases enormous amounts of energy and can briefly outshine entire galaxies. Supernova are not only visually dramatic but also essential for the cosmos. They forge the heaviest elements, like gold and uranium, and scatter them across space, enriching future generations of stars and planets. The remnants of the core collapse into either a neutron star or a black hole, depending on the initial mass. Neutron stars are incredibly dense, packing more mass than the Sun into a sphere just a few kilometers wide. Black holes, on the other hand, create regions of space where gravity is so strong that not even light can escape. The life cycle of a star is thus intimately connected to the evolution of the universe. Each generation of stars contributes to the chemical enrichment of galaxies, providing the raw materials for planets and potentially for life itself. The death of stars, while dramatic, ensures that the cosmos remains dynamic and ever-changing. Supernova remnants, nebulae, and interstellar dust are recycled into new molecular clouds, continuing the cycle of stellar birth and death. Observing stars at different stages of their life cycle helps astronomers piece together the history of our galaxy and predict the future of our own Sun. From the quiet brilliance of a white dwarf to the violent energy of a supernova, stars are not static. They are dynamic engines of creation and transformation. Their lives are long yet fleeting on cosmic timescales, and their deaths, though sometimes destructive, give rise to new beginnings, ensuring the universe remains alive with motion, light, and possibility. In essence, the story of stars is a story of cycles, birth, life, and death interwoven with the evolution of galaxies, planets, and the very elements that make life possible. By studying these processes, we gain a deeper understanding of the forces shaping the universe and our place within it, illuminating the intricate dance of creation and destruction that governs the cosmos.